The Robotic project, started in 2004, allowed the design of a complete humanoid robot to support research in cognitive systems. The robot is full humanoid, sized as a small child, and with a lot of degrees of freedom, especially designed for manipulation, for vision, sound processing, tactile sensing, and everything that is human-like has been added to the robot. The iCub has 53 degrees of freedom, most of them in the upper body. The hands have 9 degrees of freedom, and they're equipped with tactile sensors, so the robot can also feel what is being grasped. It has more or less standard cameras, but also can move the eyes, so the head is fairly sophisticated. Unlike other platforms, allows for controlling eye movements separately from the head movements and so forth. The robot is open source, both in the hardware and software, and this allowed relative diffusion of the platform in Europe mostly, but also worldwide. We have robots in the United States and Japan and Korea. Most of them are in Europe because of other European projects that supported the construction of many other platforms. They're all the same, and this allows people to share results of research, mostly in terms of software, exchange their knowledge, their specific skills, and build a community that now count more than 200 researchers worldwide.
During the eMorph project, we started with the integration of the neuromorphic sensing on iCub. Neuromorphic sensing is a disruptive technology that is inspired on how biology works. Instead of taking snapshots of the external world, the sensors respond to variations and to what happens in the environment. And this is very important in terms of compressive acquisition, because it enables to go very fast and to only transfer information when there is something important in the world. So we save a lot of bandwidth for transferring information, and also we can have a different type of computation that is based on data with wide dynamic range and with very high temporal resolution. This was the beginning of the project, and we integrated vision on iCub, but the project is much bigger because we want to integrate different types of event-driven sensing, from the skin to other types. And the video here shows how it's important to have a very fast acquisition with video for detecting salient events where a person is clapping his hands in front of the robot and attracting attention. And this can be done thanks to the speed of acquisition of event-driven cameras.
The Robot Skin project is another project supported by the Robotics unit that allowed the design of complete skin coverage for the iCub. This was let's say, later addition to the design of the platform that enabled the realization of a unique feature of the iCub, which is this artificial skin. The skin is a set of pressure sensors. There are about 4,000 sensors in the latest development of the iCub, and they allow the robot to feel contact with the environment. This is very important for a robot that has to interact with people, to interact with the natural environment, so with an environment that is completely unstructured, where objects may impact on the robot may hit the same space. The iCub skin is made of capacitive sensors. They're the same of the smartphones, basically. They're being customized to allow them to be conformable to the surface of the outer cover of the robot, and also to sense objects that are not electrically grounded, as the smartphones again. Also, we had to reduce the number of wires that connect the sensors to the main CPUs, and therefore we had to invent very specific solutions that connects all the sensors through a digital bus to the processing units inside the robot.
The goal of the KRIS project was to implement and study safe human-robot interaction, focusing on the problem of coordinating behaviors between human and robots during cooperative actions. On the iCub, we studied in particular the problem of controlling the force during interaction, and we implemented the experimental scenario that we still use today, in which the human can talk with the robot, can teach how to recognize new objects, and can show how to perform actions, physically showing how to do the actions. We replaced the components that were set at the beginning of the KRIS project. For example, we are changing the object recognition capabilities with new, more evolved algorithms, but the basic architecture is still the same.
The European project Codico aims at developing a humanoid capable of exploiting contacts with the entire body. In particular, the project starts with coping with simple contacts, like contact with the ground, and then to be able to exploit also contacts with humans. Humans are indeed very good at exploiting contacts across the entire body, but humanoids are not able to exploit contacts the same way humans do. During the project, we will develop in particular the ability to cope with rigid contacts first, and then during the second and third year to cope with elastic contacts, so compliant contacts, and finally to be able to use contact with human, so the ability to help and to exploit the support of a human, helping the robot to do an action. Humans are very good at exploiting contacts with the environment. For example, when we walk or when we want to reach for a distant object, we exploit not only contacts at the foot in order to support our own weight, but also we can use hands in order to contact the table in order to reach a far distant object. Humanoids do not have this capability nowadays, and during the development of Codico, we want to give humanoids the ability to exploit contacts across the entire body structure. A lot of foreseen scenarios are envisaged in the project, and at the end we want to be able to exploit also the support given by a human that wants to, for example, lift the robot from the ground. In this sense, the iCub is a peculiar platform because it has a distributed tactile skin that allows to feel and to perceive the interaction not only with the environment but also with humans.
The goal of the ATTACKMAN project is to study how to manipulate objects on the robot using tactile feedback. The project focuses on the development of algorithms for controlling manipulation during interaction with objects. Previous projects have developed tactile technologies for robots. ATTACKMAN starts from the results of this project and focuses only on the development of algorithms that allow robots to manipulate objects using tactile feedback. Examples of applications are to regrasp an object to get a better grip, to explore an object to recognize it, for example, to recognize the texture or the corners, and to regrasp an object using two hands, performing in-hand manipulation. And this can be useful, for example, to grasp a tool and use it in a new way.
The European project Robotics aims at understanding how robots can deal with walking in the same way humans do. In particular, we named the project after Kauravas of Elis, the first recorded Olympic champion of marathon. The project in particular aims at understanding and implementing on different humanoids the ability to cope with challenging walking scenarios, like walking on flat terrain, but also walking on rough terrain, walking on slopes, climbing up the stairs, and walking while performing goal-directed actions. The idea of the project is to exploit optimality, and in particular, optimal control methodology that allows to perform and to plan actions which are optimal from the energetic point of view. During the 4 year, it is foreseen an implementation of the theoretical results on different humanoid robots, including the iCub, but also the HRP2 and the Romeo humanoid robot. The project will, in the end, show the results and the theoretical results in a parkour scenario where the robot will go through a number of challenging walking situations.
Experience is yet another project that studies cognition. It uses the iCub but also other platforms. We've been doing 2 two main streams of research in experience. One has to do specifically with the iCub, the ability not only to recognize objects and to manipulate them, but also to learn that certain objects are useful as tools so they can serve other functions. So for instance, the robot now can use sticks or elongated objects to reach something that is out of reach, a bit like animals will do in nature, in natural environment. The second stream of research has to do more with the software development and allows now the iCub and other robots in Europe to use the same software platform to basically, we can now recycle software across different platforms and make them communicate with each other. This is important also to foster the development of a community that goes beyond the iCub. So the iCub is evolving. The moment we designing a new version of the robot is completely done internally at the Italian Institute of Technology. It's called version 3.0. It's gonna be a little taller, but also we're solving some of the mechanical problems that we noticed over many years of development. And this is only one possibility. Another direction of research in the development of the platform is to reduce the cost. In this case, the problem is that the iCub is very, very expensive. So what we're doing is to look at changing the technology so to make it cheaper. Cheaper in the sense that if we are going to build many robots in the near future, the cost will go down because the design itself has been done in such a way to use cheaper components, but also the ability to use production techniques that are cheaper by themselves. As part of the research to lower the cost of the iCub, we look into new materials and specific new type of polymers that will make the construction of the robots much cheaper. And this is another line of research that is very important for robotics. So the use of materials that are, for instance, compliant, that have controllable compliance, which means that the robot will be interacting safely with people. And this will bring about the possibility of building robots that are really useful in a normal everyday life. This is one possibility, but also there can be materials that are functionalized, which means they can carry signals, or they contain embedded electronics, or maybe they use new type of actuators that again can be naturally compliant, which in turn will enhance safety. I think the main result of the iCub project has been the development of a platform that is really shared in the research community. This is due to open source, but not only to that, also to the availability of a robot that is very sophisticated, so can fit the purpose of many different research lines. The iCub is just one possibility. I think in the future, the availability of common platforms will be very important for research. Will enable benchmarking, for instance, so the ability to test solutions across different laboratories. Will enable research in robotics to be more scientifically based, because everybody will be able to repeat experiments in different places. So it's not only paper based, so it's not only the publication of results, but also the ability to share the software, the hardware that will enable the research community to progress much faster. We'll basically be building on the shoulder of giants, which means that we will really accumulate knowledge in the future, and robotics will proceed at a much faster pace.